Classical mechanics operates on a strict, deterministic framework. If you know the exact initial position and momentum of a physical system, you can calculate all its past and future states using three irreducible dimensions: length, mass, and time. The established historical narrative places the mathematical codification of these physical laws entirely within the European scientific revolution, cemented by scholars like Isaac Newton. But examining the textual record reveals a timeline that disrupts this assumption. Centuries earlier, scholars on the Indian subcontinent had systematically outlined the phenomenological and qualitative blueprints for these exact principles. Treatises from the ancient Vaiśeṣika school of natural philosophy and the Sankhya system successfully classified physical degrees of freedom, mapped the conservation of energy, and defined the parameters of force. To understand how closely these two intellectual eras align, we are going to build a comparative matrix, analyzing the mathematical equations of Western physics alongside their earliest Sanskrit counterparts. Translating strict equations back into ancient axioms demonstrates that the human endeavor to define the mechanical laws of nature represents a continuous, cross-cultural progression. This 3D coordinate grid illustrates the foundation of kinematics. Often called the geometry of motion, this domain maps how coordinates change over time within a defined frame of reference, entirely independent of the forces causing the movement. By measuring the rate at which that position vector changes, we derive both velocity and acceleration. These are strict vector quantities, meaning they possess both specific magnitudes and precise directions in space. Motion, however, can only be measured relative to an inertial frame of reference. Under the principle of Galilean relativity, the laws of mechanics remain identical in all inertial frames, allowing us to mathematically add and subtract velocities when one frame moves uniformly past another. A full millennium before Galilean relativity, the astronomer Āryabhaṭa formulated an explicit description of this exact concept in 499 CE. To explain why human beings do not physically experience the Earth's rapid axial rotation, he noted that an observer moving forward in a boat will perceive stationary objects on the shore as gliding backward. He applied this direct observational logic to the sky, concluding that the westward movement of the stars was an illusion caused by the observer's own moving frame of reference. Dynamics takes the pure geometry of kinematics and introduces mass and force, governed today by Newton's three laws of motion. In this diagram, a vector arrow representing force strikes a static mass. Newton's first and second laws dictate that an object remains in uniform motion until an unbalanced force compels it to change, with the resulting rate of acceleration directly proportional to that applied force. This mathematical relationship maps tightly to Kaṇāda's ancient Vaiśeṣika aphorisms. He observed that motion does not spontaneously generate new motion and defined a change in momentum, or vega, as the direct result of an impressed directional force, termed nimitta vishesha. To conserve momentum in closed systems, Newton's third law dictates that every action yields an equal and opposite reaction. Medieval Indian commentaries documented this exact physical recoil under the principle of karya virodhi karma, meaning action is opposed by its effect. They proved this by observing the violent upward bounce of a heavy pestle immediately after striking a mortar. Newton later expanded his dynamic framework to encompass universal gravitation, calculating how mutual attraction draws objects toward the Earth's center, while simultaneously acting as the centripetal force holding celestial bodies in stable orbits. A moment of wonder. Looking at this original manuscript, we see the work of medieval Indian astronomers like Brahmagupta and Bhāskara II, who similarly recognized the spherical, attractive nature of Earth's gravity. They coined the term Gurudvakarṣanam. By linking the word for heaviness with the word for attraction, they explicitly defined a single cosmic pole that held planets, moons, and constellations in their specific paths. The intellectual leap to unify the downward fall of terrestrial objects with the massive orbits of celestial bodies occurred independently across two distinct eras, driven by identical observational rigor. As mechanical systems grow more complex, plotting multiple directional force vectors becomes mathematically tedious and prone to constraint errors. Take this diagram of a swinging pendulum. Analytical mechanics solves this complexity by discarding vector arrows entirely, calculating motion based strictly on the system's scalar energy values, kinetic energy, and potential energy. This phase space graph abstracts the pendulum's motion using the Hamiltonian formulation. By plotting position against momentum, the Hamiltonian represents the total energy of a conservative system as the sum of its kinetic and potential states. This model relies completely on the first law of thermodynamics. In a closed system, mass and energy cannot be created or destroyed. They merely transform from one state to another. This strict adherence to thermodynamic conservation is perfectly mirrored in the ancient Samkhya philosophical doctrine of Āryabhaṭīya, which dictates that something cannot be created from nothing. This split diagram visualizes the parallel. Just as the Hamiltonian maps an exchange of energy, the Samkhya school viewed all physical change as the continuous transformation of indestructible natural forces, specifically exchanging kinetic rajas for potential tamas. Abstracting the physical universe into a constant exchange of indestructible latent energies is a necessary conceptual leap, whether you are mapping phase space in modern physics or systematizing ancient metaphysics. Calculating an average velocity over a broad interval of time is mathematically useless if a projectile is constantly changing speed. On this position time graph, classical mechanics solves variable motion by using the mathematical limit. By shrinking the time interval until it approaches zero, the secant line becomes a single tangent, yielding an instantaneous rate of change. Centuries before the formal European invention of calculus, Bhāskara II utilized this exact mathematical concept to track the variable speeds of moving planets. To accurately map these celestial bodies, he developed the concept of tatkaliki gati, or instantaneous velocity. He achieved this by slicing a planetary orbit into an infinitesimally small interval of time called a truti, treating the speed as a constant within that microscopic limit. He successfully expressed this operation as the differential of the sine function, marking one of the earliest recorded uses of a differential coefficient in human history. The development of calculus was a mandatory tool necessitated by the human desire to track shifting celestial bodies in real time, long before it became an abstract theoretical discipline. This final data visualization table maps the direct alignment between the definitions of modern physics and their qualitative Hindu precursors. The overlap is extensive. The law of inertia pairs with nimitta vaiśeṣika. Action and reaction mirror karya virodhi karma, and the instantaneous mathematical limit aligns precisely with tatkaliki gati. Acknowledging these ancient origins does not diminish the monumental genius of the European scientific revolution. The scholars of that era pioneered the quantitative validation that defines modern physics. The strict precision of vector mathematics and calculus was the required next step, transforming a deep qualitative understanding of nature into a highly predictive industrial science. The epistemology of motion is a shared human heritage. Whether tracked on palm leaves with a stylus or calculated through abstract phase space, the logical mechanisms the human mind uses to decode the universe remain constant.